Okay, so this is the outline of chapter 24 about the electric potential. So first, of course, we will introduce the definition of the electric potential. Second, we will talk about equipotential surface, okay, which is related to the electric field lines, okay. So actually, they can be plotted in the same graph, and then the equal potential surfaces and the electric field lines actually have some relationship, okay, and and the E field, okay. So and then we will also try to calculate the potential, electric potential, due to a charged particle, due to an electric dipole, due to a continuous distribution, okay. So yes, some structure that are some sort of symmetry in between, so we can try to find its potential, and then we can actually calculate the E field. Okay, the field means the E field from the potential, means the electric potential. Calculate the E field from the electric potential. And then the electric potential energy, okay, so actually it is related to the electric potential, okay, it's the electric potential energy. And then finally, a potential of a charged isolated conductor. Okay, so first thing first, the definition of the electric potential. So here it says the electric potential V, okay, so we always use V to specify electric potential. At point P in the electric field of a charged object is V equals negative W infinity over Q sub 0. Okay, actually equals to U over Q0. Okay, so what is W infinity and U? So W infinity means the work that you would be done by electric force on a positive test charge, where it brought from an infinite distance to P. Okay, so what it means is that originally, okay, so there is an object. Okay, there are some charge distribution on it, okay, maybe uniform, maybe not, okay. So okay, it can generate some E field, of course, and we can also define electric potential for it, also in the space, but the electric potential is a scalar field rather than vector field. Here we have a test charge starting from infinitely far away, and then we try to put it close to this object, okay, and then so we will try to see, okay, so starting from infinite far away, and then we try to put it here, okay, not necessarily go in a straight line, can go from through any path. Okay, so anyway, we try to put it here, so actually we need to do some work, okay, so the work done will be W infinity. Okay, so actually this V, okay, this electric potential is defined by negative W infinity and Q0. Okay, of course the Q0 is the charge of this test charge. Okay, so so actually U is the electric potential energy. Okay, that would be stored in the test charge object system. Okay, so there will be some energy. Okay, I will say this is a potential energy U at that point. Okay, and of course we will consider U infinity. Okay, will be 0. U infinity will be 0. So actually, at infinite far away, the electric potential energy is 0 because you start from infinite far away and then put it also infinite far away, so you don't need to do any work to do so. So actually, W infinity is also 0. Okay, so I mean, yeah. For that case, okay. So if the end point is the infinitely far away, Okay, but anyway, if this point P is not infinitely far away, then okay, this W infinity is not zero. Okay, and then it defines the V, okay, at that point. Okay, so actually we we seldom use W infinity later on, okay, but we generally will use the left side and the right side, okay. So, or we try to move Q0 to the left side and then swap left and right. We will have the potential energy is equal to the charge multiplied by the electric potential. Okay, so this formula, okay, we will use it frequently throughout this course. Okay, so here we have quite a bit of formulas here. So first one is change in electric potential. Okay, change in electric potential means we try to move a charge. Okay, the starting point with electric potential of Vi and then the end point with another electric potential of Vf. So by moving this charge, you will change the potential energy. So that is the change in the electric potential energy is delta U. We denote it as delta U, which is Q delta V. Okay, delta V will be delta F minus delta I. Okay, will be Vf minus Vi. I mean. Okay, so this is the delta V. Okay, this is delta V. Okay, so yeah, so this is nothing special, I think. Okay, so or actually you can actually write W to be negative of delta U. Okay, so you just put a negative sign, okay, to here. Okay, so nothing special either. Okay, so the third one we will say it is conservation of energy. Yeah, because in a closed system we do not do any work. We do not do any work on it. Okay, and isolate it from the outer system. So we will have conservation of energy, and we also assume that there is no energy consumption between the system, so the energy can be conserved. Actually, in mechanical system, it is usually not true, yeah, because there may be frictional force somewhere. Okay, so it can consume some of the energy. So the energy may not be conserved for some of the system. Okay, of course you can still say the energy is conserved by considering the fractional loss. Okay, but it is not easy to quantify it. Okay, so but anyway, so for this kind of charge systems, okay, so we can easily assume that, okay, so there are no energy loss in between. So we will have conservation of a mechanical energy, which is delta K. Delta K is actually W, which is negative Q delta V. Okay, delta K is okay. So if you have some W, work on it. Okay, W, work on it. So work. Okay, you can change the delta K. Okay, or maybe no, not doing any work. So it is like, okay, some of the kinetic energy, okay, it should be some of the kinetic energy change into potential energy in a negative sign, with a negative sign. So yeah, so this is pretty much like this. And yeah, so the last one actually related to the work, which is like delta K is negative delta U, but you apply some work to the system. Okay, so it will be like you add the work to the negative delta U. Okay, will be the delta K. Yeah. Okay, so maybe we will, yeah, I think we will use some of these formulas later on. Yeah, but I think if you are familiar with the mechanical system, I think you should be quite familiar with them. Okay, so here let's take a look at a sample problem. So here it says electrons, okay, electrons are continually being knocked out of air molecule, 空气的分子 okay, in the atmosphere by cosmic ray particles, okay, 所以是大气层的一些空气的分子会被那些宇宙射线去把它的电子电离 okay, so coming in from space, okay, so once released, each electron experience an electrostatic force F due to electric field E that is produced in the atmosphere by charged particles already on Earth. Okay, so near Earth's surface, the electric field has the magnitude E, okay, so magnitude E, okay, pointing downwards and is directly downwards. What is the change delta U in the electric potential energy of a released electron when the electrostatic force causes it to move vertically upward through a distance d? Okay, so actually it moves upward, and then this E is here, and then a force push it upward. Okay, so it really makes sense because F equals QE, okay, and Q is, yeah, this one is a negative charge, negative E. So yeah, so the force actually points to opposite direction of E, okay. Okay, so yeah, W equals F dot D, okay, F dot D. Okay, so F here, okay, so for a charge is the electrostatic force, which is Q, okay, I mean, yeah, Q times E dot D, okay. Okay, so Q is negative E, we still keep it here. Okay, so actually equals to, okay, so we can see E and D actually points to opposite direction. So we have a Q times E times D cosine of 180 degree, okay. So yeah, so E and D points to opposite directions. Okay, so they have an 180 degree in between. So this is -1, so we have a negative QED. Then we can actually plug in all the numbers. Okay, Q is -1.6 times 10 to minus 19, and then okay, and then times E field is 150, and then times D is 520 meter. So this is nothing but 1.2 times 10 to -14 joule. Okay, so this is the work done. Okay, this is the work done. Okay, so it asks you what potential change. Okay, it also asks you what is the potential change. Potential change is actually delta U is -W, which is -1.2 times 10 to -14 joule. Okay. Not yet. It asks you the potential change, not the not the potential energy change. Okay, so actually this is not the final answer yet. So the final answer should be delta V would be delta U divided by Q. Okay, divided by Q, which is -1.2 times 10 to -14 over -1.6 times 10 to -19. So this should be a positive value. 4.5 times 10 to the 4th power. volt. Okay. That would be 45 kilovolts. Okay, 45 kilovolts. Okay. Okay. 45 kilovolts. So less than half of the Pikachu. Okay. Oops. Okay, so next we try to talk about the equipotential surface. Okay, equipotential surface. Yeah, so actually it's related to the electric field lines. Okay, so here it says adjacent point that have the same electric potential form an equipotential surface, which can be either an imaginary surface or real physical surface. Yeah. Okay, so actually you try to find the electric potential at any point in the space. Okay, so you try to connect adjacent point with equipotential. Okay, so they will form a equipotential surface. So let's say here we have four equipotential surface. Okay, 1, 2, 3, 4. Okay, V1, V2, V3, V4. Of course, we assume V1, V2, V3, V4 are different, okay, with different values. Yeah, so here it says a figure shows a family of equipotential surfaces associated with the E field due to some distribution of charge. Okay, so the work done by electric field on a charged particle as the particle moves from one end to the other of path 1 and 2 is 0. Path 1 and 2 is 0. Okay, what it means is that, okay, so here path 1 is here starting from this point and at this point. Okay, so moving this way. Okay, so both the starting point and the end points are on the V1 potential surface. Okay, so delta V is 0. Okay, so we don't need to do any work. Okay, we don't need to do any work. Delta V is 0. Delta V is nothing but V1 minus V1, which is 0. And then the second one, okay, the starting point, both the starting point and the end point are all on V3, even though the path is not lie on the V3 equipotential surface. Okay, it goes out and then go back. But for the work done, we only consider the starting point and the end point. Okay, we don't care about the path. Okay, no matter which path you go, we only care about the starting point and end point. Okay, so by subtracting the VF minus VI. Okay. Subtracting VI from VF. Okay, so for the path 2, delta V is still V3 minus V3, it is also 0. Okay, so the next one, okay, the work done as the charged particle move from one end to the other, path 3, path 4 is not 0. Okay, because for path 3, okay, it starts from V1 and then ends at V2. And then also for the path 4, okay, it's also start from V1 and from V2. The difference is that, okay, so for the V1 it directly goes from the V1 to V2 and then stop. Okay, but for the path 4, it actually go a bit off. Okay, going up to here and then go back. But finally, it also ends at the V2. So we will say the delta V for path 3 and delta V for the path 4 is not 0, but they are the same. Okay, but they are not 0, but they are the same. Okay, even though for the path 4 it go off a bit and then going back. Okay, so it say it's not zero but are identical for the two path. So that's the path 3, path 4 connect the same pair of equipotential surface. Okay, so actually here, these and these are the electric field lines. Okay, electric field lines. Okay, field lines. Okay, for this one and also this one. Okay, so the relationship between the electric field lines and the equipotential surface is like the electric field lines always perpendicular to any equipotential surface, even though the equipotential surface may not be a plane. Okay, so you can still find the tangent plane at any specific point. Okay, so that electric field lines will be perpendicular to the tangent plane at that point. Okay, 就是这个E field line 会跟equipotential surface OK 等电位面垂直就算它是曲面的话，也会跟那一点的切面 OK 垂直。Okay, so so here we comes to some more rigorous mathematics. Okay, so here we introduce another integral called the line integral. Okay, so in chapter 23 we learn something called the surface integral. Okay, here we try to learn something called the line integral. So line integral. Okay, so let's see what it is. Okay, so here we try to define the electric potential between 2 points I and F is Vf minus Vi, which is delta V. Okay, delta V previously. Okay, so here we have a definition as negative E dot ds. Okay, so even though you may consider line integral is like in one dimension, but actually it's not really in one dimension. It is not the same as something like the single variable integration, like integration of f of x dx. It is not the same. Okay, from let's say from a to b. Okay, so this is a single variable integration. Okay, so it always integrate along the x-axis. Integrate along the x-axis. Okay, so this is a function of x. Integrate the dx will be the integration variable. Okay, here what is different is that this is actually an inner product. This is a vector field. Okay, E field is of course a vector field. Okay, so this is also a vector. So ds. So what it means is that so for example on this figure, of course we have the starting point I and then the end point F. Okay, initial and final. Okay, so this is the path. Okay, so the green line is the path. Okay, so we try to integrate starting from the I along the path, along this path to the final point F. Okay, so for every so this is a curvy path. Okay, so which how can we integrate? So actually what we do similarly is we try to cut it into many small segments. Okay, so on and so forth, or maybe for this part. Okay, so this is the small ds. Okay, with this length. Okay, so for this length, suppose it is short enough, even though the whole line is a curved line. So for this small part ds we can consider is a straight line. Okay, so and then so this is a vector. Okay, ds is a vector, so the direction is actually the tangent line. Okay, so follow the tangent line at this point. Okay, so the tangent tangent line, okay, tangent direction, okay, but for tangent line, okay, it's a line with two directions, so actually the direction actually follows the direction from I to F, okay, so ds actually pointing from the I to F, okay. So this one, okay, is actually point to slightly the right to the right side. Okay, so this is the ds, and then of course for every point we have the E field. Okay, for instance, okay, so this is the E field. This is the E field. Okay, so for this part we can actually calculate E dot ds. Okay, E dot ds at this point. Okay, so E dot ds become a scalar. So and then finally we add all this E dot ds together, but we try to use a line integral to means that, or we try to add all these infinite terms together. So it becomes an integration of E dot ds, okay, from I to F, but with a negative sign. Okay, so the negative sign is independent to that. Okay, so after finishing this line integral, we multiply by -1. So it will be the potential difference. Okay. So okay, so here if we choose Vi to be 0, or maybe we can just say V or delta V is nothing but negative integration of E dot ds. Okay, so this is a line integral, so probably you won't have you shouldn't have seen it in high school physics, but in high school physics probably you also have learned electric potential, electric field. Okay, so in that sense, if we assume the E field is uniform, point to all the same direction. And then the change in the potential from a higher potential surface to a lower one separated by distance delta x is delta V equals negative E delta x. Okay, so so it still turns an integration into a multiplication. Okay, so just like integrating something like, okay, integrating 4dx from 0 to 3, just as what I always write is like, okay, so this is 4 times 3, okay, 3 will be the delta x, okay, something like this. Oh, but of course we have a negative sign in the front. Okay, so here actually the electric potential, the SI unit I forgot to mention, so actually I mentioned it here. So the SI unit for V is actually V, okay, it's V, okay, but so the full name of them are a little bit different. Okay, so for the unit it is volt, okay, volt, okay, but volt, but this V, or in this physics textbook, okay, it always call it electric potential, but in electrical engineering sense, okay, we usually call it voltage. Okay, so voltage, you can consider it as potential, electric potential. Okay, voltage difference can be the electric potential difference. Okay, most of the time voltage and the electric potential are the same thing. Okay, and then the volt is the unit. Okay, so even though PhD student in the ECE can distinguish volt and voltage. Okay, so anyways, it is easy to remember. Okay, the SI unit for V is V itself. Okay, although the full name are different. Okay, So here, so delta V, okay, so delta V has a unit of V, okay, so which means that we can consider the SI unit for E can also be V over M. Can also be V over M. Yeah, because in chapter 21, okay, in chapter 21, we know that the E field can have SI unit of N over C, okay, according to the definition of Coulomb's force. But V over M is also correct. So in the quiz or exam, you can choose either one of them, okay. So maybe some question related to this chapter, maybe well, it will use V over M. So some question related to the previous chapter, okay, maybe use the N over C, okay, but they actually are the same, okay, they actually are the same. Okay, so next we have a sample problem. Okay, so here the first part, okay, part A, 2 point I and F, okay, I and F in a uniform E field, the point line on the same electric field line, okay, so the electric field line is here, the blue line, okay, all the blue line are the electric field lines, and then this is point I, this is point F, okay, and are separated by a distance d, okay, the distance d. Find the potential difference Vf minus Vi by moving the positive test charge Q0. Okay, so this is the Q0, and then from I to F along the path shown. Okay, so actually the path in green color. Okay, which is parallel to the field direction. Okay, so this is pretty easy. Vf minus Vi will be negative integration of E dot ds from I to F. Okay, so actually it doesn't necessarily need the line integral, but just try to use it so that you don't need to be afraid of it. Okay, so E dot ds, okay, so for this green line, okay, so this is actually a straight line, so you can simply imagine ds all the way pointing downwards, okay, so along the path from I to F. Okay, so which means that all ES pointing downward, E also pointing downwards, so they point to the same direction, which means E dot ds is actually E times ds from I to F. And E is actually a constant, so which means that we integrate a constant, which means that we try to integrating, so it is like a multiplication, E times the ds is the length, okay, so from I to F, okay, which is actually D. Okay, so this is a very simple. Okay, so for part B, okay, now we find the potential difference Vf minus Vi by moving the positive test charge Q0 from I to F along the path ICF, okay. So IF and the other part are all the same, but we have an intermediate point C on the top right corner, okay. So here we try to move from I to C, okay, going right, and then going from C to F, okay, going to the bottom left. Okay. So first we go from I to C, which is VC minus Vi, okay, which is a negative integration of E dot ds from I to C, okay. So this is a straight line from left to right, So ds point to the right side all the way, and then E is pointing downwards. So E dot ds, E and ds are perpendicular together to each other. So cosine of 90 degrees is 0. So this is nothing but a 0. This is nothing but a 0. Or maybe if you like, you can actually write it as in I C E times ds cosine of 90 degrees. So this is 0. Okay, so this is 0. So this turns out to be 0. Okay. Yeah. So So going from I to C and then going from C to from C to F. So VF minus VC. So which is negative integration of E dot ds from C to F. Okay, so here ds is like this. It's like this from top right to bottom left with an angle of 45 degrees. Okay, so this is actually a right angle triangle, and then this side and this side. Okay, this is D, this is also D. Okay, so this line is actually square root of D, square root of 2D, I mean, according to the Pythagorean theorem. Okay, so here is actually integration of E times ds cosine of 45 degree. Okay, so because E and ds have a 45 degree angle between them. Okay, so cosine of 45 degree. Cosine of 45 degree is a square root of 2 over 2, or 1 over square of 2. So this is like a negative integration of E ds over times 1 over square root of 2. Okay, so finally, this is still integrating a constant, yeah, but it will be like E times integration of ds. Okay, so this time the path is longer. Okay, so the length here is actually square root of 2d. Okay, so we have square root of 2d times 1 over square root of 2. Okay, square root of 2 and square root of 2 cancel each other, so it turns out to be negative of ed. Okay, so finally vf minus vi will be, adding this one and this one together, it is still negative ed. So for sure, yeah, because we already mentioned that okay, so we actually go from this point to this point, or through this path and through the other path, they must be the same. Okay, they must be the same without any magnetic field, without any B field. Then yeah, so no matter which path you go, the potential difference will be the same. It only relates to the end point and the starting point. Okay.